The next topic we're going to talk about here is what's called collision theory. And to make a chemical reaction possible, you have to have the reactants essentially slam into each other, and they have to slam into each other with the right energy and the right orientation. So collision theory is just the study of this to see what kind of energy the reactants need and also the orientation the molecules might need to have happen. Now, in a normal chemical reaction at about room temperature, they claim there's about 10 to the ninth or a billion collisions per second. And that's a lot of collisions. Whoa. But anyway, when you have 10 to the 23rd of these little atoms and molecules running around, it's not a big deal then to have that many collisions. However, it is still kind of fascinating. So the rate of the reaction, the speed of the reaction, will be proportional to the number of collisions. And activation energy, which gets the symbol E sub A, that's the minimum energy needed to form a product between a collision between reactants. So if you don't have that activation energy in the way the molecules come together, you're not going to have any products form. They're just going to the reactants will kind of look at each other but not do anything. So once you get to the activation energy, then you have enough energy for the molecules to slam into each other and actually make products.
For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting.
So in this example, the molecules do collide, but they don't have enough kinetic energy to actually make the bond form. The N and the O there that hit each other, they're just like, oh yeah, sorry about that, didn't mean to slam into you. It's like a low collision car wreck, if you will, not a lot of damage, maybe a tiny bit to the bumper or something like that. So this is an example of when the molecules don't have enough energy to actually make products. They have to have enough activation energy if they're going to actually make any products occur.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
Many reactants have a specific orientation or geometry that has to happen to make the products form. In this problem, we're going to make nitrogen dioxide here, and the nitrogen must smash into one of the oxygens. So in this video, the oxygen on NO bumped into one of the oxygens on ozone, and the oxygens really don't have any interest in each other. It's the nitrogen that wants the other oxygen. So this has the incorrect geometry. It may have enough energy to smash in, but the atoms aren't oriented in a correct way to make the correct products.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
So in this video, the reactant molecules had the right energy and they had the right orientation. So they had enough energy to actually make the bond start to occur. They had the right geometry that the nitrogen bounced into one of the oxygens, and that's what enough to make the oxygen pull off from ozone O3 and make nitrogen dioxide with the nitrogen. So this is an example of a successful reaction, all right? It had enough activation energy to make it happen, and the geometry was correct. And you need both of them to make that happen. So sometimes scientists will create what's called a reaction energy diagram, and this is an example of a reaction between a compound called methyl isocyanide, and it's making methyl cyanide. And methyl isocyanide is on the left, and methyl cyanide is on the right down there. Carbon is the black atom, and nitrogen is the blue atom. So the isocyanide has a nitrogen between the carbons, while the cyanide compound has the nitrogen on the end. And there's a lot of information you can get from a reaction energy diagram. So first of all, it shows in this case then reactants here on the left-hand side, and it shows the products on the right-hand side. And let's just kind of look through this here a little bit because there's a lot of cool information. So first of all, notice that the y-axis is energy, and the reactants are starting at a higher energy than the products. So right away, point, you can figure out the energy required to make reactants go to products. And because products are lower than reactants, that means this reaction is exothermic. It's going to release energy because reactants are in a higher energy state than the products. So one thing we can glean from this right away is actually something related to thermodynamics. The energy is going to be released. It's exothermic. That's pretty cool. But there's another energy term here, and that's E sub A right there. And E sub A is the energy of activation, or activation energy, same thing. And notice it's a pretty high barrier that the reactants must go through in order to get to products. So those reactants are going to try so hard to get enough energy to get to the top of this energy state right here. That's called the activated complex, or the transition state. We'll talk about that more. Now, once they get to the top, then it's like going crazy. They can go downhill, no problem. But getting to that point can be pretty tough. So all reactants need to overcome an energy of activation barrier in order to become products. And that has a lot of cool uses for it, believe it or not. So anyway, but no reaction is going to be energy free. All right, you always have a little bit of energy of activation in order to make products. Otherwise, reactants would just spontaneously go to products, which would have some crazy kind of ideas. Now, along the way, you can see there's these different pictures, and these pictures show different states of the molecules as you go from reactants to products. And this is a pretty cool part about science too. I told you at the beginning of this lecture, we're going to see what happens in the arrow, what happens between the reactants and the products. Well, these little pictures here are showing what's happening between the arrow, because in the old pre-chapter 17 days, we would have said this molecule here on the left goes to this molecule here on the right with an arrow in between. But now you can see what's happening. Those bonds are shifting around. You've got this weird thing at the top here where the carbon is actually connected to the pi bonds and the triple bonds, which is like science fiction to me. Anyway, it allows the cyanide to rotate around so the carbon can then connect to the carbon, and then finally you get down to the pathway at that final product, which is pretty cool. So this is literally showing what's happening in the arrow, how you go from reactants to products. It's a pretty cool thing. This is called a mechanism, and we'll talk more about this here coming up. These reaction energy diagrams are great. It shows you right away if it's exo or endothermic. So on the right hand side here, what we have in our little diagram is the lower graph. It's exothermic. The final energy, the product energy, is lower than the reactant energy. That means it's going to be exothermic. Your delta H value will be negative because negative things are exothermic. All right. You can, though, have endothermic reactions, the top one, where the final products are higher than the reactants. That means energy needs to be put in order to make that happen. That's a positive delta H. That's an endothermic reaction. But that's important. Anytime you can talk about thermodynamic stuff with chemists, it's a pretty cool thing. At the top of that little bump there, where the top of the energy of activation, that little thing up there is called the activated complex. And you'll see some really weird chemistry when you get to the activated complex. So in this example, you can see that carbon is connected to the triple bond, the pi bond, and that makes no sense in terms of any stable molecule whatsoever. At the activated complex, you'll see things like carbons with 5 bonds, and you'll see carbons connected to pi bonds and lots of weird kind of orientations of things. So the activated complex is very unstable. It'll transfer over to the product or the reactant, depending on the energy, pretty readily, but it is kind of fun to think about as a scientist. That energy of activation, that energy gap between the reactants and the products is important. It's called the activation energy barrier, and all reactants going to products must pay this energy cost to make the transition possible. And again, without that, reactants would just spontaneously turn into products. I snap my fingers there to kind of give it extra dramatic effect. But anyway, you see the idea. Energy of activation is just a small barrier to keep reactants from going to products. And once you overcome that, then you'll have products, no problem. Some energies of activation are huge, some are very small. You can probably imagine that's going to affect the speed of the reaction, which is what this whole chapter is about. So hang tight, we'll talk about that more in a little bit. This energy of activation barrier is important. It literally is like amount of energy needed for reactants to go to products. We have a person on a bicycle who needs to get over the hill to get to the other side. And if you've ever bicycled before, it takes energy to go up a hill. Going down, though, is fun. Just whee, Anyway, I'm not a big bicyclist, but I do appreciate it. Anyway, the energy of activation is literally that way. So sometimes you'll have small bumps that are easy to get over. Sometimes you'll have big hills, big bumps that are harder to get over. And if you have a big hill, it takes longer to get to the top than if you have a small hill. So guess what? Differences in activation energy are the reason reactions vary from fast to slow. Small energy of activation, easy to get over. Big energy of activation takes a lot longer to get over. It takes more time. So when a chemist says why a reaction is fast or slow, it's due to the height of the energy of activation barrier. Now, some people on a bicycle come in full speed and it's easy for them to get over almost anything. Some people like me are more amateurs and it would take more energy. So it does depend on the initial reactant's energy, but regardless, big hills harder to get over for all people, small hills easier, stuff like that. You have to have those collisions with enough energy and the right geometry to make it happen. So you want like that person getting over the high jump thing there in order to get to the other side. Now, these reactions we've seen so far, again, are all showing as exothermic, where the final state is lower than the initial state. But you could have endothermic as well, which is really cool. Temperature absolutely affects rate. All right, and now we can begin to kind of understand what's happening. Now, first of all, let's just rewind a little bit. Rate constants K are temperature dependent. So when you calculate K at one temperature, it will be a different value at different temperatures. And now we can maybe begin to understand why this is the case. Because the energy of activation barrier is going to be the same hill regardless. But if you have a higher temperature, then you'll have more molecules able to get to the top, no problem. So the hotter the temperature, the more molecules can get over that energy of activation and become products, all right? So this is where it's cool. So there's a relationship between the rate constants K and the energy of activation, and we'll talk about this here in a little bit. But let's look at these two reactions. It's the iodine clock reaction. Both of them have iodide going to iodine. Iodine has kind of a purple color, while the iodine is colorless. And you can see the top one is basically room temperature and the bottom one is on ice.
A solution containing hydrogen peroxide is added to one containing iodide ion and ascorbic acid. This is a clock reaction, where after a small initial fraction of the hydrogen peroxide has reacted, a color change occurs. The same reaction can be performed at low temperature. Under these conditions, the color change occurs after a longer period of time.
So the top reaction, which was room temperature, took about 54 seconds to complete. All right, you can see the colorless color went to kind of this purple color. On the other hand, the bottom reaction, which was in ice, a colder temperature, took longer. It took 1:31 seconds. So generally speaking, you increase the temperature, you make the reaction go faster. It affects the rate. A scientist named Arrhenius came up with this expression, which is now called the Arrhenius equation. And this is kind of a weird equation as written, but what it refers to is it talks about the rate constant K having a dependence on E sub A, the energy of activation. So if you wish to calculate the activation energy for a reaction, you can absolutely do it. So the rate constant K equals something called the frequency factor, which we'll talk about later. You can think about the frequency factor as how many collisions have the correct geometry to make it happen. Anyway, then there's the Euler's number E. It's raised to the minus E sub A, where E sub A is the activation energy, and you divide by RT. Now, R here is the gas constant, the energy gas constant, 8.3145 joules per mole Kelvin, and T, of course, is the Kelvin temperature. So it's kind of a cool thing. When you're using using the energy R, make sure that you always use 8.3145. All right, don't use any other value for R. You'll find other ones out there, but you use 8.3145 for me in this class. Anyway, this is a cool equation because it is a way to calculate the energy of activation, the E sub A value, from a rate constant, which is cool. But what people usually do is they take the natural log of that expression. The natural log of Arrhenius equation, you end up with natural log of K on the left, natural log of A, and then natural log of e to the minus EA over RT. You can just get rid of the E part for that. So you end up with minus EA over R times 1 over T plus natural log of A. And you're like, oh, that's really helpful, Dr. Russell. Really cool. Okay, well, here's the idea. Just like what we saw earlier with the integrated first order rate law, when you can plot natural log of the concentration versus time to get a straight order, if you plot natural log of the rate constants K versus 1 over the Kelvin temperature, you will also get a straight line. And the slope equals minus EA over R. Now, R is just 8.3145, a constant. So if you multiply the slope by minus 8.3145, you will get the energy of activation. And this is considered the best way to find the energy of activation for a reaction. Now, the y-intercept equals natural log of the frequency factor. So if you want to find the value of A, you can anti-natural log e to the x, the y-intercept to find the value of A, which is kind of cool. But E sub A here is super cool for chemists. That little A thing, that frequency factor, has different interpretations, and that's kind of beyond where we need to be right now in this class. However, because some of you, I'm sure, are just dying to know, here's what I consider to be the best interpretation of the frequency factor. And so what they've done here is they've broken the frequency factor down into lots of things. There's something called the entropy of activation, which we're not going to talk about at all in this whole first year class. We will talk about entropy in Chem 223. But this is a way to find the entropy of activation, which is where they feel the frequency factor really kicks in. K sub B is the Boltzmann constant. That's the energy R constant, but per atom. So if you take 8.3145 and divide by Avogadro's number, that's the value you get there. You don't need to know that value. T is the Kelvin temperature. H is Planck's constant. We saw that in Chem 221. We'll see Planck's constant again in the future. Planck's constant, 6.626 times 10 to the minus 34 joule seconds. I talked about the entropy of activation, and the R factor once again pops in. We'll be seeing delta S again, definitely. Chem 223, we're going to hit entropy big time. Entropy is pretty cool, but for right now, just realize there is a use for the A. In Chem 222, I might ask you to calculate the value of A, but we won't be interpreting it in terms of entropy of activation or anything like that.